Test, test. Can y'all hear me and see me at home? See my shared
Yes.
screen?
Yes, sir.
Y'all are all nice and cozy.
Yeah.
Yeah. We'll get started here in just a minute. Anybody have any questions over homework or anything? All right, it's 1 o'clock. Let's get started. As I suspected with the weather that there would only be a few of you here. We're going to start 6.4 today, logarithmic functions. And these are probably some of the, well, logarithmic functions in general, I think, are some of the most misunderstood, confusing functions for students. And there's a reason why. There's a very, I hope I can make obvious reason why these are confusing. But to get to that point, I want to kind of motivate the idea of why they are confusing by reminding you about, well, what we talked about a few classes ago, and that is inverse functions, right? So the general idea of an inverse function is that if you start with a function f, which, do you remember what the conditions were on f in order to be able to have an inverse? Pass the vertical and horizontal line test, right? So it had to be 1-to-1. So as long as we have a function that's 1-to-1, then there's an inverse. And so the way the inverse works is that you have things you can plug into the original function f. Those things get spit out, and that's the range of f. What the inverse function does is it takes those things, right, and it sends them back to where they came from. So the domain of the inverse function is the range of the original function, and the range of the inverse function is the domain of the original function. So, you know, anything that is in the domain of f is in the range of the inverse, and anything that's in the range of f is in the domain of the inverse. Does that make sense? The inputs and the outputs and how they're related. So as an example, this is a very basic example. If we take just a linear function, 4x, if we graph that, it looks like, you know, a line has a slope of 4. It's 1-to-1 because it passes the vertical and horizontal line test. If we try and get its inverse, here's its inverse, 1/4 of x. So the original function f takes 1, spits out 4, takes 2, spits out 8, takes 3, spits out 12. If we want to go back and take 12 back to 3, all we have to do is divide by 4, right? We want to take 8 back to 2, we divide by 4. Take 4 back to 1, divide by 4. So that's the inverse function. How do we actually do that? Remember how we actually find the inverse? This 1/4 x, right? There was a method. Yeah, you rewrite the original function, you replace f of x with y. I did that right here. You switch the x and y variables, and then you solve for y. You'll remember that set of steps? This is important. Once you do that, you've got the inverse function. That's the way we do it, right? And we practiced that. You had homework problems like that. So now what I'd like us to consider is what we talked about last class, which is the exponential function, right? If we take an exponential function, does it have an inverse? So think about a to the x, just a general exponential function, a to the x. What do those look like again, a to the x? There was two different cases, right? We could have this, growth, or we could have decay, right? It was one of these two cases. In either case, we're one-to-one, right? These are one-to-one functions. So there should be an inverse. The question is, what is it, right? What is the inverse of an exponential function? So I have an example here for us to look at, a specific example. We'll go back and we'll look at the function f of x equals 2 raised to the x. It's exponential, right? We know it's growth because 2 is bigger than 1. We know it's one-to-one because it's exponential. So what this function does is if I plug 0 in, it spits out 1, right? Because 2 to the 0 is 1. If I plug in 1, it spits out 2 squared. If I plug in, 2 to the first power, 2. If I plug in 2 up here, I get 2 squared is 4. If I plug in 3 up here, 2 cubed is 8. But what function sends it back? See, it's not as clear as the last example, right? We took 12 divided by 4, we got back to 3. Took 8 divided by 2, divided by 4, went back to 2, right? On the previous one. It's pretty simple to see how to get backwards, yes? But here, how do we get backwards? What function is going to take 8 back to 3, 4 back to 2, 2 back to 1, and 1 back to 0? So we say, I don't know, right? I don't know what it is, but maybe we can do what we did before. We'll take this, we'll replace the f of x with y, okay? Y equals that. Then we'll switch the value, the x and y's. And now the step here is to solve for y. And this is where we run into a problem. This is where we actually run into an issue. Because in the previous problem, when we tried to do it this way, when we replaced the x and y, to solve for y was simple. We just divided both sides by 4, right? We did some algebra, right? We divided by both sides by 4. So is there any algebra that we know of that will allow you to solve for y here? And that's where we get stuck, okay? Because right now, there is no algebra that we've ever learned that will allow us to solve for this. Think about it. X equals 2 to the y. I'm trying to figure out what y is, right? I can't multiply both sides by anything. That won't help me, right? Could I divide by 2? Well, if I divide by 2, it's not going to take this 2 away because the 2 has the y on it first. So dividing by 2 does not cancel the 2's, right? Because this is 2 to the y, not just 2. So that doesn't work. I can't add something to both sides, subtract, I can't multiply, I can't divide. There's no algebra, okay? There's no algebra to do here, all right? In order to get y, or that we can do, I should say. And so I'm not going to be able to tell you what the inverse of this function is in an algebraic way. There's no way I can write it down so it's like something that you've seen before. Like this right here, 1 over 4, 1/4 x, that is an algebraic function, right? Let's just take 1/4 of that value. I'm telling you, because I can't solve for y with any algebra, whatever the inverse function is, I won't be able to write it algebraically. So I need some way to let you know I'm talking about the inverse. I need some way. So we have to come up with a new notation, all right? And that's where this whole idea of a logarithm comes in. It's just a notation that has a meaning to it. And then the meaning is the thing that's important, all right? So that's the motivation of today. Let's get to the actual logarithmic functions. So I'm going to define it first, and then we'll start talking about it, all right? The definition of this is kind of nasty to look at. The logarithmic function with base a, where a is greater than 0 and a is not 1. Does that look familiar? Wasn't that the same restriction we had for exponential functions? So this is saying if we're going to talk about it, the exponential function, we have some restrictions on a also, all right? And it's the same restrictions as the exponential function. And that's because they're inverses. So whatever one of them has as a restriction, the other one's going to inherit that same restriction. So this logarithmic function is denoted with this. Okay, so this is the new notation right here. We write log, log, we put a subscript a and then x. And the way you read this is y is the logarithm with base a, of x. All right, this is just in yellow, that is just notation. And now I need to explain to you what it means. What does this notation mean? So what it means, where's my little thing? There it is. Let's back up. Move this down. Okay, so what this notation means is that if you ever write this equation down, y equals log base a of x, what you mean, okay, what it means is that x equals a to the y. That's what it means. Okay, so that usually when I first show, it's like, what the hell are you talking about, man? All right, so let me try and explain this. If I write log y equals log base a of x like that, right? Then what I mean by this is that x must be a to the y. The way that I like to look at this, the way that I visualize logs or try and understand logs is I draw this thing called a loop or the loop. When I look at a logarithm, I always start with the base and I make this loop that goes over here and then back to the x like that, this loop, this little circular loop, okay? And what I say to myself is the a raised to this power must equal that x. So let's see how this loop works. I'm going to write down a. So let me write down a. I'm going to raise that to the y. And then that must be equal to this x right here. And do you all see that is that equation right there? This right here is that. That's how I remember this relationship. I just take the base, I raise it to the other side of the equation, and I set it equal to what's here. So let's evaluate a couple of logs just to make sure we understand like what's going on here. So look at these expressions. Look at this first one. 1.23 equals m. Right now, what we would consider this to be is an exponential statement because you have something raised to a power equals something, right? That's all of these have the same property that it's something to a power equals something. What we want to do is convert this, change it to a logarithmic statement. So the way we do this is you think about that loop. Let me bring that loop down here. All right, so right now what we're looking at is an exponential, this is an exponential statement, which would be equivalent to this side of the equation over here. We have some number, in this case, the x is like the m, the a is the what for us? The 1.2, and then the y is the 3. You all see that? I want to convert from here to this. So I'm going to write down, I always start by writing a log, okay? And then I need the base of the log, which is the number that's going to go down here. The base of the log is always the base of the exponent here. So that's 1.2. That goes here. And then I put an equal sign, and I kind of think about the loop here. There's this kind of imaginary loop that goes like this. And it says raised to that must equal that. So when you look at this, what am I raising the 1.2 to over here? What am I raising? What power am I raising the 1.2 to? 3, right? So that's going to be the other side of the equation is going to be 3. And then that must equal, so what is it equal to? M, right? So that M goes here. That is the equivalent expression. These two things mean the exact same thing, all right? These two expressions mean the exact same thing. They're just written in different formats. The first format is called exponential form, and this is called logarithmic form. Do y'all see that if I take 1.2 and raise it to the 3rd power and set it equal to m, I get back the original thing? If you're confused, let's just do another few of these before we finish. Right now, all we're doing is looking at the two different notations. All right, we're not trying to solve for anything. I'm not trying to figure out what m is. I'm just converting notations. Let's do this next one. All right, so for us, I want to convert this to a log, right? So first thing I'm going to do is I'm going to write down log. What base am I going to use for the log? E, okay, so I put E here, then I put an equals, and then I start thinking about what this would have to be raised to be equal to this. So what am I raising E to? B, that's going to be on the right-hand side of the equation, B, and then this must equal 9, right? So this means the 9 goes here. With me? Let's do the next one. You try this one on your own. So the base, A. What goes here? Not the other side of the equation. What goes here? 24.
24.
Yep. 24. And then the other side of the equation is the 4. Okay, good. Now, again, let me just restate. All we're doing right now is introducing this new notation that has this meaning. We haven't seen like how we're going to use it or anything else. Just new notation. Okay. Now, let's try and go the other way. What if I give you a log expression and I can ask you to convert it to exponential? These, I think, are easier because all you have to do is use that little loop I just gave you. The loop, I mean, you just do the loop. So for this first one, log base A 4 equals 5. I apply the loop. I'm going to take that, raise it to that, and set it equal to this. And so that would give me what? A to the 5th power equals 4. That is the equivalent exponential statement of that logarithm. This one? E raised to the -3 equals B. You could read it the other way around also. B equals E to the -3. It doesn't matter which order you do it in. So I'm raising it to that, and it equals that. And then the last one is 3 raised to the C equals 5. Are there any questions? Do you all agree these are easier than the other way? Okay, because all you have to do is just apply that little loop. All right, so Let's go back. Just, I'm going to take a little break here. Go back to where we were on that problem earlier. This one right here. We were sitting here right now, right? And we were saying, hey, I don't have any algebra, right? That's going to allow me to get this y solved for, right? I can't do anything that's going to solve for this y. However, if I now take this and ask you to put that into exponential form, logarithmic form. Let me go back right here, put it in here. If I were to take that and say, hey, put that into log form, you would write log, and then you need a base and then equals something. You're gonna raise that and then come over and put there. So what's the base I'm gonna put here? 2. So 2 goes here. What goes on the other side of the equation? Y. And then what goes here? X. Do y'all see that? Y equals log base 2 of x. Wait a minute. I just solved for y, didn't I? Don't I now have y by itself? Yes? Okay, but what the heck is this, right? What is that, right? What is that function? What is it? Like, it's something now, right? That is the logarithmic function that has a base of 2, but what is it? What does the graph look like? And there's a lot of things. The main point here, the big point, all right, that I want you to take away from this is that now we have a way, right? We have a way of solving for the y, right? We have a way of getting the y out of the exponent and down by itself, but it requires we introduce this thing called a logarithm to do it. All right, any questions on the loop and just the notation and converting back and forth? We're all good at home? Y'all okay?
Yes, sir.
Okay. So now the next thing. Since we now have this idea of this loop, we're going to work with the loop. We need to see what is it that we can actually do to make sense out of this logarithm. So look at these examples. Find the exact value of this logarithmic expression. So I'm going to start with this first one. It's saying log base 2 and 16. Notice there's no equal sign here. It's just asking me to figure out what log base 2 of 16 is. So the first thing I want you to think about is, like, what the hell are they, what do they want, right? Like, what is it that this is asking me to do, right? This is like a new language, and I'm not quite sure what this is saying. So I want you to think about this. This wants an answer, right? There's an answer to this. I'm going to call that answer x, okay? I don't know what it is yet, but it's x. Now convert it to an exponential form. So if I convert this to exponential form and use the loop, what does my new equation look like? 2 raised to the x equals 16. Good. Now look at that equation. I realize that the x is up in the exponent. Okay, I realize that the x is up there. But can you tell me what power I raised 2 to in order to get 16? Like 2 to what power? 2 squared is 4. 2 cubed is 8. 2 to the 4th is 16, isn't it? So one way I could do it is just by looking at it and just saying, oh yeah, that's a 4. Or I could do this. I could write the other side of the equation is 2 to the 4th power, right? 16 is 2 to the 4th. And so what I can do is I can say, oh, well, then these two must match, right? In order for there to be equality between these two statements, if they both have the same 2 down here, then I would need this to be this x to be a 4. So now I can just say, oh, well, then x must be 4. And that's the solution. So what I'd like to do now is I'd like to go back to the original problem, and I'd like to write down what we just discovered. Log base 2 of 16, we said the answer was 4, right? That's the answer. And you can check it for yourself right now with the loop. 2 to the 4th power is 16. 2 to the 4th power is 16. So listen to the words coming out of my mouth, all right? When we had this original problem right here, okay? What that was saying to me is this: figure out what you raise 2 to in order to get 16, right? That's what that's really asking me to do. Figure out what power I'd have to raise 2 to in order to get the number 16. And the answer is 4, right? So look at the next one. Oh, you know what? Let's not do that one yet. Let's do an easier one. What about this one? What if I write log base 7, 49? That's asking me what? In just English, right? And just speaking to me, what is that asking me to do? For what number do I need to raise 7 to in order to get 49, right? So 7 to what power is 49? Do we know? Second power, right? Second power. So 7 to the second power is going to be 49. Just remember, right? It's raising it to this power must be equal to this number. Let me give you another one. What about log base 7 of 7? Tell me in words what that's asking for. Someone at home?
What number do you raise 7 to get 7?
What number do you raise 7 to get 7? Okay, Tavi, what number do you raise 7 to get 7?
1.
1. Right? 7 to the first power. So that's not 7 times 1, right? That's 7 raised to the 1 is 7. Good. Let's keep going. What about log base 7 of 0? Ooh. Oh, you know what? Hold on. Y'all aren't ready for that. Let's do this. Let's do 1. All right. That's 0. I kind of gave it away. It's saying, what power do I raise 7 to, right, in order to get 1? So over here on the side, if I'm thinking through this, I'm saying 7 raised to what power is 1, right? That's what I'm saying to myself. 7 to what power? This one was saying 7 to what power is 7. This one was saying 7 to what power is 49. Do you see those? So the only power I can raise 7 to get 1 would be 0. Yeah. Okay, now I'm going to try and plug 0 and see if I can mess y'all up. Log base 7 of 0. That's asking me this question. 7 to what power is what? 0. What do you think?
Undefined.
Yeah, we can't do it. Why?
You can't, no matter what, an exponential function can't even go to 0.
Exactly. Good. So what's being pointed out here is that if you look at the left side of this, 7 to the x, think about that as like an exponential function, right? We know that exponential function, if we graphed it, would look like growth or decay. Growth. 7 to the x would look like this, wouldn't it? If we graph that function, 7 to the x. And what we are asking is, when does this hit the x-axis? That's what that's really asking, right? And if we try that, we're going to get nothing because it never hits the x-axis, right? It never hits the x-axis, which means that this is undefined. There is no answer to that. In fact, wouldn't that be the same result if we tried to plug any negative number in? Think about that. If I say, what's log base 7, and then I tell you in here, put a negative number, what's going to happen? You're going to say, okay, that means 7 raised to what power equals a negative number? And what can you tell me from the graph of 7 to the x? Is it ever going to spit out negative numbers? No, right? It's always above the x-axis. So it's impossible for 7 to the x to ever give me a negative number. So this would also be undefined. Does that make sense, everyone? Now, I will summarize that later, okay? We actually are gonna have some domain restrictions on the log function, but we'll get to it in a minute. All right, so let's look at this one up here. Log base 3 equals 1/27. Ooh, okay. So let me see, what is the question that's asking me? It's saying 3 raised to what power is 1/27, right? Isn't that what it's saying? Can anyone just look at that and tell me? -3, good. Now let's see how we get that. What we're going to do is we're going to rewrite the 27. I recognize that it's 3 cubed. So I have to recognize 27 is 3 cubed. And then what I'm going to do is I'm going to say, all right, well, wait a minute. Anytime I have that, I could bring the 3 to the third up to the top as a 3 to the -3. So I'm using properties of exponents that if you ever have a negative exponent, you can drop it down below 1, right? I'm using that property backwards. It's down here with a positive exponent, so I push it up to the top with a negative exponent. And now these have the same base, right? They both have 3. And so all I need to do is make sure that the exponents match. And to make sure the exponents match, we get x is -3. So the answer to this is -3. What do you think? Does it make sense or not? Let's do a few more. See if I can get you all confused at all, or more confused. How about this one? Log base 10, no, log base 100, 10. What is the question it's asking? Somebody at home, tell me what question this is asking.
X to what power gives you 10? Oh, sorry. 100 to what power gives you 10?
100 to what power gives you 10, right? That's what it's asking? 100 to what power gives you 10? Oof, how the heck am I going to do this? In the previous problem that we did, where is it? Right here, right? This one right here, when things weren't very nice, what I tried to do was get them to both have a base of 3, didn't I? And then I just matched their exponents up. Is there something I can do to get both of these bases to be the same? Now let's try and go with the smaller number. We have 10 and we have 100. Is there any way that we can rewrite the 100 with a 10? Ten squared, right? We can do 10 squared. So watch, can I do 10 squared to the x equals 10? Isn't that the same exact problem? Yeah. 100 is 10 squared, and then I'm raising that to the x. All right, now properties of exponents. What happens if I take a number and raise it to a power and raise it to a power? What do I do to these powers? Multiply them. Okay, don't add, multiply. So isn't this the same as 10 raised to the 2 times x is 2x? And that must equal the 10 over here. What's the power on this 10? 1. And now do you see that you have the same base? And now you just need those exponents to match, don't you? So that means I can write down that 2x must be 1, which means x must be a half. When you raise something to the half power, what's that the same as doing? Square rooting. Half power means square root. So what we're saying here is that the answer to this is a half. Let's just check it just to make sure that this answer works. If I take 100, raise it to the half, do I get 10? Well, that's the same as the square root of 100. And yes, indeed, that is 10. All right. So it works. Any questions? There's going to be plenty of these in your homework to practice. All right, let me give you one more. Well, you know what? Yeah, let's try this one. Log base 8 of 4. Yeah, let's go with that. Log base 8 of 4. I'll go to my students at home again. Somebody tell me what is the little thing I'm trying to do here? What's the little thing I'm asking myself?
3 or 4.
Asking 8 raised to what equals 4?
8 raised to what power x equals 4? Okay. Now, as we had before in this problem, I tried to get the 10, I tried to look at the 100 and the 10. I said, look, maybe I can find something they have in common. They're both powers of 10, right? And so I was able to work through this. Here I have a 4 and I have an 8. Is 8 a power of 4? No, it's a multiple of 4, but it's not a power of 4. So I can't do what I just did. I can't say that 8 is 4 squared or something like that, right? But they do both have something in common. What can you tell me about both 8 and 4? They are powers. They're both powers of 2. Isn't 4 2 squared? And isn't 8 2 cubed? Right? So could I write it this way? 2 cubed to the x equals 2 squared. And what does the left side become? Using the same thing we did a second ago, something to a power to a power. 2 raised to the what? 3x must equal 2 raised to the 2. And now we have the same base. And we have these exponents must match for this to be true. So I set up a little equation, 3x equals 2. Divide both sides by 3, and I get x is 2/3. So the answer is 2/3. Sorry, I should just put that up here, 2/3. See, that's not as obvious, right? I mean, if you look at that, you can't just look at, well, some people can, but most people would look at log base 8 of 4 and be like, okay, 8 to what power is 4? 2/3? Yeah, I don't think people are going to come up with that right off the top of their head, but you can solve it, right? Like you can work it through. One more, promise. Well, maybe not. I won't promise anything. Okay, let's try this one. Log base 3, 5. So the question we're asking ourselves is 3 to what power is 5, right? 3 to what power equals 5? Now, 3 and 5 don't have the same like base. Like you can't do what we just did in the previous problem, right? Like the 8 and the 4, they both were powers of 2. 3 and 5 are both not powers of 2, are they? Or powers of anything. So what, right? What do we do? Do you understand the conundrum we have here, the issue? Like, doesn't look like there's much I can do. I mean, in this one, we had 10 and 100, so they were both powers of 10. Here, these were both powers of 2. In the previous problems, let me see here, I was able to rewrite this. They both were powers of 3. Here, they're both powers of 2. Here, that, you know, this was, well, this I just looked at, right? 49, but that you could look at 49 as being 7 squared. 7 to the first power. So it looks like we finally have hit a roadblock, okay? And in fact, we have. We can't do this yet. We will be able to do it today, but we can't do it yet, right? So this, we're stuck, right? We're stuck. I can't tell you right now what power I need to raise 3 to in order to get 5. All right, I can't tell you, couldn't tell you. So as much as we can figure out, there's a lot we cannot still. All right, back to the notes here. All right, so let's talk more about logarithms in general. Like just if we start to look at a logarithm as a function, right? Then when we write something like log y equals log base a of x, just remember the loop, right? That right there, really, there's a loop that goes with this. But let's try and conclude what it is that we can and we cannot plug in for x. I want to talk about the domain. So what did we say we couldn't plug in? What did we try plugging in before and we had issues? Couldn't plug 0 in, right? Because let me rewrite this in exponential form. This is a to the y equals x, right? That's what this is in exponential form, written with the loop. A raised to the y equals x. If I'm going to talk about restrictions on x, we said that there's no way this could be 0 because an exponential function can't be 0. So domain or x cannot be 0. What else? Could we have negatives here? No negatives, right? Because again, an exponential function can never be negative. So not only can x not be 0, x has to be greater than 0, right? Can't be negative. So do you see right here in the notes, it says the domain of a logarithmic function, right, equals the range of the exponential is 0 to infinity. That's the important part. We can only plug positive numbers into logs. You're not allowed to plug a 0 in. You're not allowed to plug negatives in. All right. Also, the range, what comes out of a logarithmic function is everything. Now, the reason why it's everything, and this goes back to the picture from earlier in the class, if we have an exponential function, a to the x, whatever the domain of this function is, in the range, the inverse function, right, which is this log function, right, that's the inverse of this, it undoes it, is actually the domain and the range switch places. So the domain of the inverse function is the domain and range switch places. So if I'm asking you what's the domain of the inverse, right, then I really want the range of the original function. And that means what's the range of a to the x? And when we look at that picture of a to the x, it's either that or that, right? The domain of this function, the inverse, is the range of this, only positive numbers. And then the range, right? The range of this function, the green one, right, is the domain of A, but the domain of A is all real numbers. So they switch places. That's all this is saying. The domain and ranges switch places between the two functions. That's basically everything I just said, written a different way. All right, let's take a couple of logarithms and let's figure out if we can figure out what their domains are. So I'm going to write down this first function. It's capital F of x equals log base 2 of x plus 3. Hey, real quick before I forget, y'all are all aware that next week, right, next Wednesday, I will be in Houston. My wife's having surgery. I told you all about that, right? Or no? I think I mentioned it a while back. So next Wednesday, my intention is to not have a Zoom meeting and not have a face-to-face class. Instead, what I'm going to do is I'm going to give you an assignment where you are to watch a video. I won't make it a 2-hour video. I'll just tell you to watch a short video. And then I'll give you an exercise to do that'll be turned in based on that video. Are y'all okay with that instead of me having a sub? I don't want to like upset anybody. I can have a sub come in, but I can tell you if I have a sub, they're not going to be streaming Zoom, so everyone will need to be here. Anyone
I
object to
would
my,
say the video's better.
you're okay with the video?
Yes, sir, in the assignment.
Yes.
Okay. If anybody has any objections, please email me. If you don't want to say anything now, email me. Let me know in the next day or two. Also, while I'm talking administrative stuff, next week is the drop date deadline is next Friday, I believe. So late, that's the last time opportunity for you to drop a class, a 16-week class. So this is not just for this class, just if you're taking any other 16-week classes, just so you know, next Friday, the 12th is the last day to drop a class and still get a W in the class. If you want to drop a class, there's a way you do it online, but at the least, and this is just, again, if this goes for any class you're taking, at the minimum, email your instructor by 5 o'clock on Friday and say, I would like to be dropped from the class. If you have that documented, then you should be okay. All right. If you have, if anyone's in, not sure of how to do it or something. We're not going to have any more grades between now and then. So you kind of are at that point where you have to make that decision for yourself, like how you feel about the class. Also, if you go on to Canvas, you'll notice today, I took all of the homeworks that you were doing online and I made all those homeworks worth 0 points. And then I created a new category called homework. I think it says homework all. And I gave everybody full 100 for that. So basically everybody right now has 100% on their homework, which is 15% of your course. So I guess what I'm saying is that where you stand in the class right now, if you look at your grades, the only real thing that can impact you is the next 2 exams. Your homework is maxed out. It can't get any better. So use that information however you need to make a decision. All right. Questions? I'll send instructions on the video and all that sometime in the next few days. Monday I will be here though. Okay, Monday I'll be here on campus and we'll have classes normal. All right, so here we go. We want to find the domain of this. All right, so here's a logarithmic function. This is our first actual like true logarithmic function here. Right, we're written out capital F of X equals this, and we're asked to find the domain. Okay, so please note the instructions. Find the domain. So what I know about logarithmic functions is that I have to plug in positive numbers. So that means that whatever's in the logarithmic function, this right here, must be positive. That must be bigger than 0. And this is a linear inequality, so all I have to do is subtract 3 on both sides. And I get x must be greater than -3. Which written in interval notation means -3 to infinity. That's the domain. Pretty simple, right? Because the inside of that logarithmic function was linear, so it was pretty easy to solve. The next one's gonna be a little harder. So for g of x, this is what's inside the logarithmic function, right? That whole thing. So we need to make sure that that whole thing is bigger than 0, right? That's what we need. Now, what type of inequality is that?
Rational.
Rational. And what were the steps to do this? To solve it? This partly what was on your homework, or at least this was a concept that could have appeared on your last test. There's kind of different ways to approach this, but I said to just treat this kind of like a rational function and think about what you know about this. Now, I'm not going to go through all the steps to graph it. I'm just going to do the basic steps. The basic steps are, if I were to graph it, I would have an x-intercept where? -1. That's where the numerator is 0. So I know I'd have an x-intercept at -1. Where would I have a vertical asymptote?
+1.
+1. So set the denominator equal to 0, you get +1. You got that, right? And what we're asking is, when is this thing bigger than or bigger than 0? So all I need to do now is maybe pick a couple of test points, maybe here, here, and here, and see if I get positive or negative numbers out when I plug them in here. So let's try a number over here, -2. Let's try 0 is a good one. And then how about 3? Let's plug those in and see if it's true or false. So if I plug in -2, what do I get on top? Negative. If I plug in -2 on the bottom, I get a positive. Be careful because you're doing 1 minus -2. It's 1 plus 2. So you'll have a negative on top and a positive on the bottom. That's negative, isn't it? Is negative bigger than 0? Negative number is not bigger than 0, right? So that means nothing over here should work. Then you plug in 0. If we plug 0 in for x, we get 1/1, and 1/1 is bigger than 0. So that should work. Anything in here should work. And if I plug in 3, on top I'll get 4, and on the bottom I'll get a negative number. So a positive divided by a negative is negative. That's not bigger than 0, so this should not work. So only numbers where? Between -1 and 1. Do I include -1 and 1? No, because I do not want this to be 0, right? If I plug in -1, I'm going to get 0. I don't want 0. I want it bigger than 0. And I can't plug 1 in because 1 is basically, it's undefined at 1. So the domain of this up here, I'll put the answer up here, is going to be everything between -1 and 1. That makes sense, everyone? How about this next one? This one's a little tricky. Log 1/2 of absolute value of x. Think through this. Maybe it'll help if we know it. Do y'all remember what the absolute value of x looks like if you graph it? Looks like a V, right? That's what the absolute value of x looks like. And we just need to make sure that whatever we do here, whatever comes out, whatever this absolute value of x is, we just have to make sure that it's positive, right? It can't be 0 and it can't be negative. Will this absolute value function ever spit out something that is negative? No. Will it ever spit out 0? Yes. Where does it spit out 0? At 0. So we got to make sure we don't plug 0 into this log function, because if we plug 0 in here, we're going to get a 0. And you can't plug 0 into log. Now, any other number, doesn't matter if it's positive or negative, once we take the absolute value, the log function will be happy. So this is everything except 0. So I'd have to say -infinity all the way to 0, union everything from 0 on to infinity. This answer up here was -3 to infinity. Does that all make sense, everyone? At the end of the day, for all of these log functions, if you're asking for the domain, all you're going to do is take what's inside the function and you're going to set it greater than 0 and solve. It might be a linear inequality. It might be a rational inequality. It could be a quadratic inequality. There's a lot of things it could be, all right? While I'm talking about this, I want to make a point to you. I want to tell you something, because I know in pre-cal my students always struggle with this. If you have a log function and inside of it you put, let's say, x squared plus 1, okay? This thing inside the log function, whatever's inside, is called the argument. Whoops. Oh my gosh, what's wrong with this thing? Stop. The argument of the function. And that goes for any function. If you have a function and then inside of it you're putting an expression, whatever it is, that's called the argument of the function. You'll see in pre-cal, when you study what are called the trig functions, you'll study the sine function, cosine function, the tangent function, and you'll start plugging things into those functions. And you'll probably hear your professor say, oh yeah, what's the argument of that function? It's the thing that's inside is the argument, all right? All right, any questions on domain? All right, what do graphs of logarithmic functions look like, right? What do the graphs look like? So there's a bunch of properties here. Let's just get down to graphing one, okay? Let's graph one. So we have not done this. Do y'all remember how easy it was to graph an exponential? Like we really liked it, didn't we? Because it was just make a little table, and then maybe we would have to do some shifting up, down, left, right, reflect, whatever. But compared to rational functions, we were so happy, right? Well, the good news here is log functions are actually pretty easy also, all right? So the way that you do a log, I'm just going to make one up. Let's do log base 2 of x, all right? Here's the way I'm going to do this. I'm going to make a t-table, all right? These are going to be my x's, and then here's my function's value. Now, you know, on exponential functions, what we did is we all picked the same numbers, -3, -2, -1, 0, 1, 2, 3. And I said, everybody use those same numbers, right? For log functions, not that easy, all right? It's going to be a little bit different. What we're going to do is we're going to look at what the base is, okay? We're going to look at whatever this base is, and we're going to plug in things over here that are powers of this base. And I like to start with 0. So what would 2 to the 0 be? 1? What would 2 to the first power be? 2. What would 2 to the second power be? 4. Then 2 to the third, 8, 16. Do y'all understand what I'm doing there? I'm just looking at the base and thinking about numbers that are powers of that base. Now let's try a couple of negative powers. What would 2 to the -1 be? 2 to the -1, let me write down the side. 2 to the -1 would be the same as 1 over 2, which is a half. So I'm going to put that here also, a half. Now try 2 to the -2. That would be 1 over 2 squared, which is 1/4. Let's do one more. What would be 2 to the -3? 1 over 8. If you do this, then getting these function values should be easy. Because think about where they came from. How did we get the 1? How do we get 1 here? What did we do? We raised 2 to what power? To 0, right? Well, wait, isn't that what this is asking me? Like if I go right now and I try and plug 1 in there, I'm going to say log base 2 of 1, right? That's what it's asking. That's just saying 2 to what power is 1? Well, 0. That's where it came from. We generated that ourselves. The next one is log base 2 of 2. So 2 to what power is 2? 1. What's log base 2 of 4? 2. Log base 2 of 8. 2 to what power is 8? 3. And then we can keep going, right? The next one will be 4. The next one's -1. The next one's -2. The next one's -3. Now these are points, right, on my graph. So this is the point 1, 0. This is the point 2, 1. This is the point 4, 2. This is the point 8, 3. Next one's 16, 4. 1/2, -1. 1/4, -2. And 1/8, -3. And I'd like to put those on a graph. Now I know what this graph is going to look like, so that's why I'm drawing it like this. Well, you should know why I'm drawing it like this too. Why am I not drawing anything to the left of the y-axis? Yeah, we have a domain restriction, don't we? I mean, this log function, you cannot plug any negative numbers or zero in. So I'm not going to have any picture over here at all. Now I'm going to start plugging in or start plotting these numbers. The first number, the first point here, sorry, plotting these points, is 1, 0. That's go out to the right 1 and then don't go anywhere. The next point, 2, 1 means go to the right 2 and then go up 1. The next one, you go to the right 4 and then you go up 2. The next one, you go to the right 8 and up 3. I'm going to run out of room. Y'all see that? So far, here's what our graph looks like. If we were to connect these, our graph looks like this. Okay. And then I need to plot some of these. So 1/2 -1. Think about what this means. Move to the right half and go down 1. So go to the right 1/2 and go down 1. That's this one. The next one, I go to the right, how much? 1/4 and go down 2, right? So go to the right 1/4 and go down 2. The next one, I go to the right 1/8 and go down 3. What does it look like is going to happen here on this side right here as I get closer to the y-axis? Yeah, it's going to get closer and the graph just keeps diving down, right? Back with rational functions, we called this a vertical asymptote, didn't we? It's exactly what's happening here. The closer we get to the y-axis, the more we're forced downward. And yes, in fact, we do have a vertical asymptote right there. That is the graph of that log function. Questions? By looking at the graph, can you see the domain? 0 to what? To the right forever, right? 0 to infinity. What about the range? Doesn't this graph go down forever? And up forever. Now, look at the way this graph grows. It grows like this, and it goes slowly. It is slow growth. Logarithms grow slowly, but they do grow forever. Now, I'm going to go to some graphing software because I want you to see the logarithmic function graphed by a computer. Okay, you'll just have to trust me that that's the graph. And then what that log function, see, is this the one? When we plugged in 1, we got what? 0. When we plugged in 2, we got 1/2. It's hard to see it there, but yeah, there we go. 2, we get 1/2, 0.5. When we plugged in, what was the next one? 4, we got 2. Or 4, we got 1, sorry, right? This right? Hold on.
I thought it was 14.
Oh, I put the wrong thing here. I'm sorry. I put the wrong thing there. There we go. All right, when we plugged in 2, what did we get? 2 was 1, sorry. 2 was 1. When we plugged in 4, we got 2, right? We plugged in 8, we had 3. Sorry, I had the wrong graph up there. Make sense? This is the graph. Now, think back from when we started class. This is the inverse of an exponential function, isn't it? It's the inverse. It's the inverse of which function? Which one? Because this was log base 2, right? That's what we just graphed. So it should be the inverse of 2 raised to the x. If I graph 2 to the x right now, we should see a graph that is a reflection over the identity. Oh, let me put the identity first. Remember that diagonal line? Okay, let me graph 2 to the x. There it is. Do you see that 2 to the x is this exponential growth, right? And this is log base 2 of x. It is the inverse of that. Perfect reflection over the diagonal. Now, if I change this 2 to the x to, let's say, 4 to the x, it's no longer a perfect reflection. What would I have to change this one to? Log base what? 4, right? If I do that, now they're perfect reflections. So for every exponential function, there is a corresponding logarithmic function that is its inverse. You change the base of the original exponential, you have a change of a base in the log. Make sense? Now I typed in here something else. Just ignore this right now. If you're looking at it going, what the heck are you doing? Don't worry about it. All right. I'll explain it later. All right. So that's how we graph those. Let me go back to that note then. Let's see if this makes sense. For any logarithmic function, the domain is only positive numbers, right? Like we can't plug in any negative numbers. And then the range should be everything. What about the x-intercept of the graph? Shouldn't they all have this point? Should they all have that point 1, 0? Think about it. If I plug 1 into any log, and we talked about this earlier, if I take any log you want, log base anything, and I put 1, oh, hold on. Sorry. Okay, if I put 1 here, what is this asking me? What's the question? A to what power is 1? Or A to what power is 1? 0. All the time, right? No matter what A is. No matter what A is, this should happen. Which means that if I plug in 1, I should always get 0 for any log. Which means this point right here should be on every log function I ever graph. We had something similar to this when we did exponentials. Remember when we did exponentials, we said that this point would always be here? The point 0, 1 would always be on every exponential. With logs, we have the same thing. We'll always have 1, 0. What's the next property? Oh, it's decreasing if A is between 0 and 1 and increasing if A is greater than 1. Let's go back and look at our graph. Look at the red one. Let me take these out of here. Is that function increasing or decreasing? It's increasing, right? Now, if I change the base, let me change it back to what we started with. This was log base 2, right? That's log base 2. Now, what if I change that base to a number between 0 and 1? Let me show you what happens. Actually, I'm going to make this A, and I'm going to create a slider, and then I'm going to make the slider go from 0 to 4, so you can see the difference here. And then I'm also going to graph A to the X. There we go. There we go. May as well put this one back. Okay, so this is what we had, right? This was log base 2 of X. Here's its inverse, right? 2 to the X, and there's the diagonal. We talked about in a previous class what happens to the green one, right? If I change the base, we said if you make the base get bigger, it's going to grow faster. And what happens if I go less than 1? Where does it go? The green one starts going the other direction, right? Like that. Well, look what happened to the red one. Look what happened to the inverse. The log. What did it do? Instead of it doing this, right, increasing, it now decreases. Only focus on the red one. Decreasing, increasing. Decrease, increase, right? Also, no matter where I move it, this is actually kind of cool, like right in about here, because they're still reflections of one another, aren't they? Over this diagonal. You reflect the red one over, it lands on top of the green. Reflect the red one, it lands on the green. So that's what that node is saying to you. The node is saying that if you do a logarithmic function and a is between 0 and 1, you're going to decrease. If a is bigger than 1, you're going to increase. Ignore this. I'm not worried about this. Also, the graph is smooth, continuous, no corners, no gaps. Okay, so you can draw it, it's nice and smooth. All right. A special log function. So we talked last class about a special exponential function, right? The special exponential function was the e to the x, right? E to the x was the special one that we had last time. F of x equals e to the x. And I tried to explain why in calculus that's such an important function. But if we take its inverse, right? Its inverse function would be this right here, wouldn't it? It would be the log function with base e. That's what it would be, right? Let's see what happens here. E, if I graph e to the x. So there it is. The green one is e to the x, and the red one is the log base e. Now, somewhere at some point in time, people decided to stop writing this log base e function like this, all right? They said, you know what, let's stop doing this. And instead of this, we're going to use this, all right? So like, I just want you all to understand, because this is important. Up to this point, if I wanted to write a log function, I explicitly need to put the base down there for you, right? I tell you what the base is. Yes, log base 2. These are all log functions, and the base is very easy for you to see. 4, 5, 7, 2, right? If I wanted to do log base e, that's what I should write, yes? But we don't write that. Instead of that, we write this. Now, what that stands for, that's L and then N. Okay, so really that's an L and then that's an N and then X. The L stands for logarithm, the N stands for natural. So like in French, you would say that logarithm natural. So that's why we write ln instead of nl. Natural log, we say log natural. Now, the reason why we do this, okay, there's a historical reason behind why we do that. I wish this never would have happened. I wish everyone would have just stuck to this, because students forget that this natural log function, oh, it's called the natural log. I didn't put that here. Sorry, it's called the natural log. The natural log function, okay. I don't like this, okay, because students forget what the base of this function is. They forget, first of all, they know it's a log function, but they forget the whole idea of the loop and all that, because it's not written down here. So historically, here's why. The natural log function is it comes up so many times in research, physicists, chemists, biologists, when they're doing these studies on things, this natural log function kept on coming up, just like the e to the x was something very important, appeared naturally. The natural log comes in a lot. And so back in the day, think about, I know everyone here is probably not old enough to remember, and I myself personally only used a typewriter when I was, I think, in elementary school. My parents had a typewriter. Like, I mean, so typewriters are, I don't think, have any of y'all used a typewriter before? Y'all know how they work? You have to like load a piece of paper in, turn a drum, and you type, and these little like metal prongs come up and basically stamp the paper, right? And that's the way a typewriter works, right? So you're typing. Well, back in the day when typewriters were being used, this natural log function was appearing in these research papers, and maybe the research paper was, 200 pages long. maybe the natural log appeared in there, I don't know, 400 times. And so on a typewriter, if you have to subscript, right? If you have to actually go in there and physically subscript that E, right, a little bit below, then you'd actually have to stop typing, turn the drum a half turn, click E, and then turn back and then continue typing. And that's a real pain in the ass, right? As you imagine, if you had to do it like hundreds of times. So they said, look, instead of doing that, let's just do ln x. Everyone will understand that you mean log base E. And then when you're typing, you don't have to stop. You just keep going, right? So it was convenient, right? And even today, if you use a word processor, subscripting is not hard, but it is an extra step, isn't it? Like you can do like a shortcut macro or something, you can do something, but it requires more than just typing. And so natural log of x, because it appears so much, we have a special notation for it just to make typing easier. So please don't lose sight of the fact that the natural log function, that abbreviation, that notation is simply this. There is a loop. The loop has E down there, right? Just don't forget that, all right? Now, there's another special log function. The other special one. Now, the natural log is the most important, okay? Other special one. And that is this one, log base 10 of x. And that one also appears quite a bit, all right? That appears quite a bit because it's log base 10 and our number system is base 10. We talked about the fingers, right, in class, 10 fingers. So this comes up quite a bit. So what we decided is, you know what, same thing. We don't have to type and turn the drum and all that. So instead, we're just going to write logx. We won't put anything down there. And you need to remember it's a 10. I think it's kind of like when you write the square root of 4 like that, that's not the same as the cube root of 4, right? Those two are different things. Everyone knows that's 2 there, right? It's understood. If it's anything other than 2, you have to put the number. That's the way this kind of log works. If you don't put a number down here, it's understood to be 10. If you need it to be something else, you better put the number there. If you want it to be E, right? If you want it to be E, you won't even use log, you'll use ln. So those are the two that have special notations for them. And on most calculators have a key for both log, and for ln, both of them on most calculators. Okay. I'm not going to say anything. I'm just going to see if, just from what you've gathered today, can you solve these equations for x? From what I've taught you about the whole idea of the loop and all that stuff and everything we've done, can you figure out how to set up these equations and solve for what x is? I'm going to give you about 5 minutes to see how far you can get with these. I'm going to take a quick break. I'll be right back. Any ideas here? So I didn't give you any examples. I just want to see if you could maybe figure this out. Saying yeah? Okay.
I think I got it, but I'm seriously worried that I got it so quickly.
Okay, so what did you do, Carissa? For the first one?
So I changed it to the exponential form, which is where
Okay.
I set the 3 to the power of 2 equal to 4x minus 7.
There you go. Yes, exactly. Use the loop to create that. Now you have an equation. All right, and it's linear, right? It's just a linear equation. If you square the 3, you get 9. 4x minus 7. That's what you did?
Yes, sir.
Okay, that's it. Yep. Now we can just move the 7 over. We'll add 7 to both sides. Divide by 4. And you get x is 4. There you go. Good. Does the other one work the same way?
Very similarly.
Yeah, the equation's a little different, but let's do it. You're going to do the loop. So you've got what, x raised to the second power equals 64, right? Now we have to be a little bit careful here, a little bit careful, because when we solve for x here, there's a couple ways to do it, but I think maybe most of you would just do square root on both sides here. Now, when you do that, you have to do plus or minus, right? Because you initiated the square root. So you do that, and then this is plus or minus 8. Are these both solutions? No, why not?
-8 is not in the domain.
Okay, so you're right, but be careful on the language there. So we have two answers, 8 and -8, right? -8 is not okay, but it's not because -8's not in the domain. It's because look at what x is, right? X is the base of the log. And the base of any log, right? If you take a log, the base has to follow the property that it's a positive number and not 1. The x has to always just be positive. So it's not the fact that it's negative and we can't plug negatives into logs. It's because the base of a log has to be positive. Now, had the x been where the 64 is, then you could say it's because it's not in the domain. See the difference there? Or understand the difference? So I just went to the restroom when I took a break. There's a video on YouTube of like a city council meeting where, I use a wireless mic, right? So when I leave, I have to mute my mic. So there's a city council meeting where one of the guys in the city council has his wireless mic on. He goes to the bathroom and he forgets to turn it off. And it's over the whole intercom system. Like, it's hilarious. Just look it up online. It's pretty funny. You see like someone, like jumps up and runs after him or something. Okay, that makes sense? Solving equations? This? I wanted to give you another one before we do that one. We're kind of getting short on time here, but how about this one? How about natural log of x equals 3, and then log x equals 0.2. Can you solve these for x? So I'm going to just work through these with you, but I just want some help on this first one. What am I going to do on this first one? Convert the log to an exponential, right? So I'm going to use the loop to do that. What's the loop though? E to the 3. See, this is where that notation is bad because you're supposed to understand that this really means log base E, right? So you have to do that loop like this. So this is E cubed equals X. What about the other equation? $10, right? So there's a 10 down there. It's not written, but it's 10 to that equals this. So we have to do 10 to the 0.2 equals X. Now, those two you can do on your calculators, right? Do e cubed on your calculator, you'll get a number. Do 10 raised to the 0.2, you should get a number. I'm not going to get these. You can get those decimal answers. I just wanted to show you one illustration where this notation can be a little tricky if you forget what the bases are, right? All right, so how about this equation? Solve it for x. So I recommend you switch this to a log first. Switch it to a log. We switch it to a log. It's log what base? E. Okay, then I have an equals, and then I think about what the loop would be. So what goes on the right side of the equals? 2x, and then what goes on the left side? Or left side of the equals? 5, right? Now, log base E is really the natural log, right? This is really the natural log of 5 equals 2x. Yeah? Now, here's where, and we're going to do a lot more of this next class. Here's where we're going to break out our calculator. And we're going to use our natural log key on our calculator to figure out what natural log of 5 is. So make sure you have your calculators. Try this. You find your natural log key and do natural log of 5. And when I do that on my calculator, I get on the left-hand side 1.6094. It goes for a long time, but I'm just going to go the 4 decimal places. 1.6094, and then I'll just divide everything by 2. And I get 0.8047 equals x. All right. Questions on that one? Like I said, we will talk more about your calculator and how we can use that. How we're going to use the calculator to solve these problems. Remember, we still have a question I asked early in the class that we still have not been able to solve. Where is that sucker? No. Where'd it go? Where is it? That one. Remember this one? 3 to the x equals 5. We still don't have a way of doing this. We will next class. I'm not going to be able to get to it today. All right. Let's talk about the homework. Remember how I'm doing this now, right? I'm sending this file out to all of you. It has this homework assignment here. I've already gone ahead and highlighted the yellows here. I know this looks like a bunch of stuff. I would say do it to the point that you feel comfortable with it, right? I mean, you don't need to do all of these, but first set is convert the exponential to log, okay? And then the next one is convert the log to exponential. So you're just going back and forth between the two forms. These, you're actually trying to figure out what these are, exactly what the answers are. So I did a few of these in class, like 2 to what power is 1? 1/5 to what power is 125. This is where you make the bases look the same and try and match the exponents up. See how that goes? This next section is domains. The next section, it asks you to graph these functions. I would say, yeah, try these two. Okay, you're trying to graph the log functions. Graph them together with the exponential functions. See how this goes. Now, 65, 67, and 69, I didn't talk about, but I figured you might be able to figure this out because all this section is about is transformations. Like once you know what a log is, what it looks like, these involve just shifting left, right, up, down, reflections. See if you can match 65 to which function it would be. And then the last group, I highly recommend you do these. These, there's no instructions here. Solve for x are the instructions on these. Solve for x. Okay, solve for x. All right. We've got 10 minutes. I know y'all are ready to go, but I wanted to save 10 minutes for something. I'll try not to take the whole time. This is an off-topic but on-topic thing. You remember how we were talking about the base 10 number system? And that's where log base 10 is important stuff. So base 10, what base 10 means is that in our number system, we have 9 digits. I'm sorry, 10 digits. I'm losing it. All right. Right? In our number, if in the base 10 number system, there are nine numbers and 0, right? All numbers in our number system are made up of those digits, right? So if I write a number like 345, what 345 means is that I have 5 ones. This is back to grade school, right? I didn't show you all this, right? 4 10s and 3 100s. Right, that's what it means. Okay, another way I could write that is 3 100s would be 3 times 100, right? Plus, now 4 10s would be 4 times 10. And then 5 ones would be 5 times 1. Agreed? If I do 300s plus 4 10s plus 5 ones, I would get 345. Now check this out. This is the cool part. Every single one of these numbers here, 110 and 1, those are all powers of 10. Watch. This is 3 times 10 squared plus 4 times 10 to the first plus 5 times 10 to what power? 0. So when we write 5 in the first digit, this is how many 10 to the zeros we have. When we write 4 in the second digit, this is how many 10 to the first powers we have. If we write 3 in the third digit, this is how many 10 to the second powers we have. Understood? Now, what if I add a decimal to this? 0.21. If we follow this same pattern, then this should be plus. This should mean that we have 2 10 to the what powers? -1, right? Because look, 2, 1, 0, going backwards, this should be -1. But what is 10 to the -1? That's 1 over 10. So isn't this saying you have 2 tenths? And haven't we always said the first decimal place represents how many tenths we have? And the second decimal place is how many hundredths we have? So the next piece would be plus 2 times 10 to the -2. 1 times 10 to the -2. This is how many hundredths? Got it? That kind of makes sense? Now, that's base 10. Base 2, you only have 2 digits, 0 and 1. Okay, so every number I make up can only be made up of those numbers. So if I write 1 0 1 0 1 1, if I write that in base 2, what I mean is this. I have 1 what's. Okay, so let me go back. When our first digit here, the 5, said we had 5, whatever the base was to the 0, right? And then 4, whatever the base was to the 1, and then 3, whatever the base was squared. Understand? So this should be 1 what? 2 to the zeros. Okay, this next one, 0, should be, I have 0 what? 2 to the 1s. This means I have 1 2 to the 2. This means I have 0 2 to the thirds. Here I have 1, 2 to the fourth. Are you following the pattern here? Last one. 1, 2 to the fifth. Yes? Now, what is 2 to the 0? 1. Okay, so I have 1 times 1, that's 1. Got it? What's 2 to the first power? 2 times 0? 0. Okay, so that's 0. Plus, okay, 2 squared. 4 times 1? 4. Plus 2 to the third? 8 times 0? 0. Plus 2 to the fourth? 16 times 1? 16 plus 2 to the fifth? 32 times 1? 32. Add these numbers up in our base 10 number system. 48, 52, 53. This is equal to 53. This number is what we call a binary number. It's base 2. This number in binary is equivalent to the number 53. Okay, so that number 100101 is not 110,101. Written in base 2, it's equal to the number 53. One more thing. How many different base number systems are there? As many as you want. We use base 10 because we have 10 fingers. We use base 2 because computers only understand on and off. So 0 and 1, the only 2 states that anything can be in. But if you look at like, well, I won't get too much into it. There's another base called hexadecimal. Hexadecimal. Do you all know
I
what
learned that in Java.
Yeah. So do you know what the base is for hexadecimal? What's that?
I want to say 32.
It's 16. It's actually base 16. I'm pretty sure I'm right on that. It's base 16. All right. What the heck? Okay, so in a base 16 number system, how many different digits can you have? 16, right? Because base 10, you had 10. What were they? For base 10, they were 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? For base 2 is only 0 and 1. Here we have 16 of them. So we have 0, 1, 2, 3, all the way till I get to 9. But then once I get to 9, I can't say 10 because 10 is just a combination of a 1 and a 0. So I have to use a different symbol. So we use letters. A, that's the 11th, 12th, 13th, 14th, 15, 16. There are the 16 possible digits of a hexadecimal base 16 number system. I can use any of these I want to create a number. So watch me create a number. I'm going to create the number C2E1. What is that number in base 10? So let's see if you can wrap your head around this. This means we have one what? 16 to the zeros, right? Because the base system here is 16. Plus, what is this one? This is the tricky one. E, 15, because this is 1, 2, 3, 4, 5, 6, 9. This is like 10, 11, 12, 13. Wait, hold on. 14, right? This means we have 14 what's? 16 to the ones. And then this is, let's see, I have 2 what's here. I have 2 16 squareds. And then here I have C. What's C for us? 9, 10, 11, 12. I have 12 16 cubes. Now you'd have to get a calculator for this because I can't do that. 16 cubed times 12 plus 16 squared times 2, 16. Someone do it for me. Oh, we're out of time. Someone can do it. Or I can just go to a website that'll do it. Can someone tell me what the letter was? Or what was it? C. 49,800, say it again, 49,889. This is what that number is written. This is base 10 version. This is hexadecimal. So there are advantages and disadvantages to the different bases systems. If you've ever seen that movie, Martian, is it Martian, where what's his name gets stuck on Mars, right? And he's trying to communicate. What's his name? The actor? Matt Damon. Yeah, and he's trying to communicate with people back on Earth, but he only has a certain number of positions he can set this dial to, and he realizes if I want to be able to communicate and I only have these certain positions, then I think there were 16 positions. He's like, I'll just use hexadecimal. I'll convert everything to hexadecimal, and that way I can communicate easily. And that's what he did. So anyways, this is kind of a random thing, but it's when we talk about the base of a log or base of an exponential function, the E is important because it has to do with calculus. The 10 is only important because we are in base 10 finger wise, but there's all these other systems out there that we use in computer science, base 16, base 32. All right, y'all have a great day. Do your homework. See you next week. Have a good weekend.
Bye, sir. Have a good one.
I think
Bye-bye.